Recording in progress.
Excuse me. All right, good afternoon, gentlemen. Well, I'm just letting you know beforehand, I don't know what is happening. I'm having some internet issues, but we will soldier on. Won't be long today. There are just two topics I believe we have left. We need to look at transformer protection and generator protection. All right? So I want to talk about the transformer today. I made an effort to go through your exam. Okay, I'll just comment briefly on it. All right. So in terms of, let's start with question 1. I don't know if you have access to that. I just uploaded the information. Maybe I have it locked. Anyway, let's start with question 1. It seems obvious that me asking a theory question may have thrown you. I get the impression you weren't expecting something like that. Be that as it may, we asked and we highlighted the word fully explain. Some persons may have overlooked that, but I think all the information is in your notes, so I don't need to spend too much time on that. All right, so the correction that was being pointed out at the time of the test was the IET instead of IEC, but I trust you would have appreciated that it's IEC. Yeah. All right, so what were the key things in this question? Firstly, what we're trying to find is VEF. When we looked at the example for CT selection, all right, we used both what was happening in terms of calculating VGH. You remember that? So we calculated VGH, but we could also use the excitation curves in order to find VEF. So VGH would have considered the relay and the connecting wires, while VEF would also include the secondary resistance of your CT. All right. So I think where I saw maybe one person making the error is that with the 355 top, the individual went ahead and used 0.125 a second time instead of using the 0.168 for that. What is it? 350? How about all that? There's no 350 on this. Oh, there was no 350. All right. So how did I see that? How did I miss that? Anyway, there is no 350. How did I miss that? All right. Well, for those who use the 300, hold on. That means I may have done somebody a disservice. Let me just check my let's see. Okay. All right. Yeah, so so Buchanan, I owe you a couple marks. Just a couple. Yeah. I will not penalize the other people, but I owe you a couple. I overlooked that. All right. And you actually pointed it out, eh? So Johnson, I hope I am the only lecturer telling you this. But you look like you need to carry a typewriter to the exam.
Yeah. Yes, I'm aware the handwriting was off, sir.
Yeah, I can't read.
Apologize for that, sir. I'm going to be using ruled paper next time.
Yeah, please do. Yeah, it's difficult to read. Okay, you hear me that nice one?
I've been Air Foods today, sir.
Okay. All right, so that was question one. Question two. Nothing scary about that one. I don't think anybody struggled with that. All right. Since you're a close-knit group, I suppose I can speak specifically to persons. No, Mr. Buchanan, I appreciate your desire to be accurate. But when you're in a position where it is impossible to estimate, them 20% that you're estimating to get 120 milliamps. I was just waiting for you to look up to verify that you wear glasses. But even with the best lenses, it's kind of hard to make that sort of estimate, all right?
Yes, sir.
And that is a lesson in of itself, because to an extent, that is what you're going to have in protection, right? Where you will never be able to get the exact number. Right? Just in some texts, you will see them talking about, some of their opening comments would be that, I think it's in Blackburn, that protection is a science and also an art. Right? So some things you will just have to round up. You wouldn't be able to say that it was 120 milliseconds or 90 milliseconds. Right? So I'll just make that note. All right. Question 3. Gentlemen, listen. When I say me highlight certain words, it's because it's important. So when I say explain and I put explain in bold, I'm looking for more than the definition. All right? I note I said more than the definition. So obviously the definition needs to be a part of the answer. So having defined it, for some of the scripts I may have asked you, I may have put therefore. So you define it, but the question asks, how does it affect the operation of an electrical network? Right? So, keyword here. I think only one person really, well, come to think of it, I didn't hold you to accountable with part B, because it talks about discussing the relative merits. There's a difference between listing and discussing. So some persons listed, some persons mentioned, some persons defined. Right? At this level, we need to understand the difference between these. If I ask you to discuss, it means that you would have stated the particular merit or the particular benefit, and then speak to how that benefit impacts operation. All right? And the others, well, I don't think I need to go through that. With respect to the last one, I think all of you got it. I can't recall. I think only one person put the VT over the CT and therefore got 6/5 instead of 5/6. I don't remember who it was, but one person did that. All right. But for the most part, everybody, I think, understood the question. So I must admit I was expecting some 80s and 90s, but I'll work with it. This is your first assessment. You have a taste of what a protection exam looks like, and so you should be okay going forward. You have any questions or concerns regarding the paper? All right. So one of the things I picked up though is that, I want you to, I know that the material is quite bulky. I will admit that. But it's important that for protection, you understand why you are doing what you're doing. Excuse me. All right. So this is a little more than networks, where you apply to procedures, or even in power systems, you have some formulas, you just know when to apply them. You really have to understand why you're doing what you're doing with protection. All right. So I believe this is already posted in the lecture notes, but I'll just go through it and talk a little about transformer protection. Mr. Johnson, Mr. Duncan, I sent an invitation to you for the OER. Either you're interested? Did you see it?
Yes, sir. I sent a message to you indicating my interest. Okay. Did you see it, sir? Well, probably not. Since
you sent it via Schoology?
Yes, sir.
All right, I will check later on. I haven't seen it. I know I saw Mr. Buchanan. Oh, all right. Yeah, I see this. Okay. All right. Whoa. All right, so I passed that on. So, we're talking about your transformer. And we know the purpose of a transformer. Transformer is simply there to connect two systems of different voltage levels. That's its real purpose. It also helps to isolate the network in terms of separating the network, right? And this is done by use of the different windings. So we have our delta, which causes zero sequence to stop at a particular point in the network, etc. So transformers are a very important piece of equipment, right? Yes, we appreciate the different voltage levels that it facilitates, but as I just mentioned, there are other uses. So it's important that we try and keep this particular part of the power system in operation, and we must seek to protect it appropriately. Now, you have gone through your machines, you have gone through those modules, and you understand how a transformer works. You understand the basic operation, right? The mutual inductance and that sort of thing. You understand about the core, what's the real purpose of the core. You understand about losses associated with your transformer, right? You have your I2R losses, you have your core losses, your winding losses. You understand all of that, okay? What we are now going to be doing is to put that component in the power system and look at one, its construction, its operation, and see how we go about protecting this component or this part of the system. Okay. Now, depending on the use of the transformer, you can use a fuse as protection, or you can have, as we are saying here, an elaborate protection scheme. So in terms of fuse, if you look on the pole-mounted transformers, you would usually see a fuse protecting that. Okay, it's not that it's not important, but in the scheme of things, that's good enough. You also now have deployed across the Jamaican network what we call self-protected transformers, right? SPTs, and these transformers have a breaker on them, right? And when they malfunction for whatever reason, then you would see a red light on the transformer itself. Okay, so you can have those. You can have with your fuse, etc., etc., etc. But then you can move now to having a transformer where you are monitoring almost everything that the transformer does. You're looking at whether or not it's getting too hot. You are looking at on the taps. You are looking at whether or not there is gas being produced, and all of these will tell you that something is happening with the transformer. We're dealing with a power system. We're talking about protection, which means that at some point, whether as a result of service or fault, you're going to lose power on the system. The transformer is an electromagnetic device, and therefore it relies on the flow of current for its magnetism. So when you have a power outage, the question is there enough magnetism, right, remaining in the core of the transformer? Those things we have to look at, because the normal protection that we apply to your transformer, or one of the standard forms of protection that is applied, is differential protection. However, when you're energizing a transformer or re-energizing a transformer, what you're going to have is that and this now depends on the amount of flux that is retained in the transformer core. You're going to have current being drawn by the transformer to build the magnetic field within the core. But you're not simultaneously getting an output from the transformer. Now, if we recall how the differential system works, that in of itself should suggest that you have a fault. But based on what we know we're doing, we are just re-energizing the system. There's no fault. So we're going to talk about that. So we look at all of these things. We look at some of the possible fault conditions that may occur and how they are mitigated. All right. So that's part of what we call that elaborate scheme, right? As I said before, your differential protection is one of the methods, or one of the common methods used for transformer protection. Now, in terms of continued operation, a fault that is created in any part of the network on the line, right? The fault current will have to pass through the transformer, because the transformer, technically speaking, is taking power from the generator. And so the generator has to provide that fault current. Okay? Now, because you have the fault on the network and the fault current is passing through. Now, given that if it is that the fault is not on the transformer, it's external to the transformer, that fault current, when it passes through, would not necessarily trigger the differential system, because it is seeing the same current coming in as going out. And I know that sort of sounds funny, given that we know that the primary and the secondary currents of the transformer are different. But in terms of the turns ratio we use for the CTs, right, the current on either side will become the same. But going back to what I was saying, now, although you're having the fault current passing through the transformer and not tripping the differential system, which is there to protect the unit, you have to also take into consideration the impact that high current is going to have on the transformer itself. So can the transformer handle the fault current? If it can't, we therefore have to find a way to protect it. So in addition to differential, we also have overcurrent protection for your transformer. All right. So even in the event that the fault is not on the unit, you want to ensure that currents above a certain level will not be allowed to pass through the winding. Now, it may not be evident, but large fault currents can have a mechanical impact on your transformer. Right? In the same way, low voltage or low frequency can have an impact on the transformer, a mechanical impact on the transformer. We'll talk about that. So, differential provides the best overall protection. Right? And of course, we have already spoken about high impedance grounding, which helps in terms of the providing unit protection where the possibility of saturation of your CTs exists. All right? So the transformer in this case would be that unit. We looked at it generally to say you have a true fault, right? And the impact it may have on your CTs. And so we spoke about the high impedance grounding. So that we call it my general introduction. So your winding faults are going to be dependent on the earthing resistance. And you have already proven this with your lab one, where when you change the neutral earthing resistance on the transformer, you also change the fault currents. So as you increase that neutral earthing, then you are going to reduce the magnitude of the fault current. But of course, and we will look at this in more detail when we think about the generator. But if you are going to reduce the fault current by increasing the neutral resistance, you have to bear in mind that if you are then using earth fault protection and you are reducing that fault current, that you are running the risk of it not operating as quickly as you would wish. You with me? So it's again, it comes back now to the science and art. I know I can reduce the fault current by having the earthing resistance. I can increase that earthing resistance, but by increasing the earthing resistance, you're also reducing the fault current that will go to your relay. You understand me? All right, I hope you do. All right, the leakage reactance, which comes down to the unit itself, the transformer itself, and of course, where on the winding you have the fault, right? Because if you know where the fault occurs means that you will be having a certain percentage of the winding voltage being used to create the fault. So the closer you are to the neutral point, then the lower will be the current, because you're tapping off a smaller portion of the winding. All right. The other thing we need to think about would be the windings that we have. Now, our focus, for the most part, would be on star and delta, but I just want to throw in the mix. We're not doing machines, but just throw in the mix that you also have other winding configurations, such as zigzag. So, but for our purposes, we're talking about star and delta. All right, so in terms of information, just drilling down now where the impact of the winding is concerned. Right? So if you have a star connected and a grounded star, yeah, through an impedance, the current will be dependent on the value of the earthing impedance. And we have already said that. Right? And it's also impacted by the distance from the neutron. Okay? So the further away we go from the neutron, it means that we are tapping off more of the winding, so you get a larger voltage, and by extension, a larger current. But quite frankly, whilst this is all true and this is all the theory, it is really not that important, because once we have a winding fault, it means that it's going to create it's going to create a problem, for the transformer, and it's going to manifest itself depending, or the way in which it manifests itself will be dependent on the magnitude. So if I have a large winding fault or a significant winding fault, then yes, it's on the oil, but it's going to impact the oil differently from us having what we call insidious faults, meaning it's there and just gnawing away, like how the fox gnaw at the grape, at the vine. All right. There's nothing I need to add to the other one, but you can take it. So in a sense, in summary, and the points we are making here, is that the faults are going to be impacted by the type of winding. Right? I'm not expecting you to try and figure out or try and recall what the individual impact will be. That's not our purpose. Oh, by the way, Mr. Johnson, I need your address. What else do I need? I need your address to complete that.
Email address?
No. Yeah, I need that for the function tomorrow, but I function Thursday.
My home address.
Yeah.
Okay.
All right. So this is basically what we're saying. Is that the fault current is going to depend for a winding fault, going to be dependent on where on the winding the fault occurs. Right? So we have our neutral point. Here we're showing it being tapped off in the middle. So that fault current would be less than if the fault was out here, because it means that you'd have tapped off a larger portion of the winding. Right? In terms of voltage. I know in terms of impedance, you're saying, well, you would have a larger impedance. That's true. But you'll be taking off more of the system voltage at that point. All right? All right. In terms of the information I gave you in that second bullet, right, regarding the primary current, that's what we are showing. So the distance of the fault from neutron, not a one-on-one relationship, obviously. But as I said, the important thing is to note that the fault current is going to be impacted on where on the winding we're getting the problem being created. I think these are in the notes, so you can refer back to the notes for these. Okay. The second point we had made is that the leakage reactants, right, determines the fault current. And this now is quite different from the figure I just showed you. This is in relation to the primary current. In terms of the reactants, the leakage reactants. So if you recall, when we talk about a transformer, we give the leakage reactants the X value, whether that 0.16 or that 0.2 per unit. That's what we're referring to here. Yeah. All right. So in terms of the relationship, again, we're not asking you to try and record these. All right? Just for you to understand and appreciate that there is a relationship where the fault occurs, as well as the winding, the type of winding that we're using. So all that we have spoken about thus far has to do with your star. For your delta, all right? So in terms of the magnitude of the current, that is kept below your rated current value. Again, my focus here for the delta and the star is just for you to appreciate that there is a difference between the fault current depending on the type of winding that you're using. When we're looking at the use of star and delta in power systems, what we focused on is the impact it had on the zero sequence current. All right? That no zero sequence would move across the delta. What we are now saying is that we're now focusing on the magnitude to say that that will vary based on the type of winding that we're operating with. Sure, you all right?
Yes, sir.
You look so tired.
Sir, I just have a headache, that's all.
And it's not because you check Schoology before the class, eh?
No, sir, I didn't check Schoology.
Just making sure. Making sure I did not have anything to do with the headache.
Yes, sir.
Okay. For obvious reasons, you will hardly have this occurring. But remember, I said earlier that those through faults, if they are not properly managed, can have mechanical impacts on the transformer. Now, if we go back to the basic principles of transformer operation, you know you have a core, right? But that core, if just left as a big solid piece of metal, would increase your losses in terms of eddy currents, right? And so what is done from what you would have known from high school? Remember that thing with them about lamination, right? Those big transformers that you see in the substation also have a laminated core. What is done is that, unlike the little transformers that you would pick up and have and see the laminations, which are then glued back together, for those transformers, the core is then bolted back together, right? So the core is bolted back together. So it's laminated but bolted. So if it is then exposed to all these external shocks, which although created electrically, have a mechanical impact, what you can end up doing is to loosen those core bolts. And it is in those circumstances that you're going to end up having winding faults. Because otherwise, there are well, not really, but there are no moving parts in a transformer that we all know. Right? So there has to be that external factor which may cause the fault between phases. So more than likely that would be occurring outside. But be that as it may, should we have one inside, we need to know how to treat with it, or know its impact, or understand its impact. Right? Now, one of the, and it's almost every time I get to this point, I'm thinking that, you know, there are some modules that we have removed from our diet, which we may need to bring back. One of them is high voltage engineering, where you know, you get an appreciation for you get an appreciation for something that you would have been doing from first year. When you were talking about dielectrics. Remember you were talking about dielectrics from 6-1? Right? It's the same basic principle that we are using here for these high voltage pieces of equipment. So for some transformers, depending on the size, right? Some transformers, based on the size, you may use for insulation what we refer to as impregnated paper, which is just paper soaked in oil. All right, so those are dry core transformers. Right, so some transformers you go and when you open it, all you see are the windings separated by some paper like material. But then you also have transformers whose core or whose insulation comes from oil. And we are saying here that you can have that insulation breakdown due to external short circuits. So as I said before, although the fault is not on the transformer, you have to manage the magnitude of current that will pass through it. Because if you have the fault external to the unit still has to carry the fault current to the fault point. Are you with it? So you have to manage what passes through. All right. We talk about, well, again, this I use it here in terms of steep front-end impulse voltages. May come from lightning strikes. Now, we looked at transients. Yes? And we looked at the fact that depending on the connection at the load point, when you energize a line, that you at some point may have a doubling of the voltage. Remember when we did that? With all the reflection and refraction and all those things?
Yes, sir.
Now, what we did not speak about was the characteristic of the waves. So you'd have a similar waveform, all right, for a switching as well as a lightning pulse. However, the difference between the two would be in terms of the rise and fall. So one is a lot sharper, one is a little more gradual. All right. So the impact of these steep front impulse voltages, which comes from whatever transient, whatever noise, which I'm defining here as an unwanted signal, impacts the system, right? It can cause damage. Let me keep it as simple as that. It can cause damage to your transformer. This is just an English thing. In reading your test just now, one of you, I think, used the word damages. Damage is never pluralized unless you're in court. All right? So when you use the word damages, it is the payment you get or the ruling that is handed down. The penalty handed down in court. That's damages. Otherwise, it's damage. Don't worry. They taught me the difference when I was about your age, so don't feel bad. All right? Okay. So you can't say I didn't teach you something in English. Okay. So in terms of the relationship, again, I need to take these slides out because it's not something I expect you to consider. So let's talk about interturn faults. All right? And these now are those faults. You have a winding, but of course, you know that the material that is used to make the winding is insulated. You're aware of that, right? So it's insulated and it's an insulation medium. Now, interturn faults means that the insulation on the winding itself becomes damaged, and you then end up with a hot spot. All right? And I mentioned hotspot because here and now is the danger with these interturn faults. Right? It may continue and just get more severe. Now, if you recall, when we spoke about your protection, when we introduced the protection system, and we spoke about the relay, we said that the relay was used to either initiate separation or to send an alarm. Okay? Now, these faults are the type of faults that you want to send an alarm for. Because they will start slowly, but if left unchecked, will escalate to big things. So you want to be able to manage these faults. And I know that Mr. Johnson have some exposure to the utility company. And when you go down to system control, sometimes you would wonder if these guys should really be getting paid, because it seems that if all they do is sit around and talk and chat for part, right? And watch a computer screen. Work kind of look boring. But the truth is, Why it's so important is that you must be able to detect or pick up when little problems start to arise. Right? So you have to monitor the system. So it's not just looking at these pretty screens and you see something like Power World and that it look all nice and fancy. All right? You have to be able to determine when the abnormalities are coming in by way of alarms. Right? Because it's best to manage the start of these faults than to allow them to escalate so that you have to remove the transformer or you're forced to remove the transformer. It's best to go and do your switching, take out the transformer, have it repaired or whatever you want to do with it, and then restore it to proper operation. So these faults, they are interturned, but they will not necessarily be reflected externally in terms of the currents flowing into the transformer. All right? And that's one of the reasons that they are really, really dangerous. But there's a way to detect them. All right. So in terms of issues that may impact our transformer, overload. We have a transformer, but understand that there will be occasions that you have to overload a transformer. However, what you are given is a time limit. So you're not going to routinely overload the transformer. However, in operations such as switching, you might be doing some switching, you will have to overload a transformer. But the proviso is that you do so for a limited time. Right? So overloads can mess with the transformer. System faults, and we have spoken about that. Over voltages. Right? And we know voltage is a function of, or let me say it the other way around. Insulation is a function of voltage, right? Reduce system frequency. So let's just talk briefly about how each of these will impact the transformer. For your overload, it's going to cause increases in your copper loss. And therefore, you're going to get more heat being produced. So you have transformers which are force-cooled. Right? So we have fans that are on the transformer or come as an accessory for the transformer. And a damaged fan, a fan that is not working, should trigger an alarm. So you're going to monitor the temperature. So as I said, in terms of the overload, yes, you increase the copper loss. But at the same time, we are saying, even with this ill effect of the transformer, right, you can have an overload for a limited period of time. All right, do we have this? Okay. So in terms of the fault current and considering the time that we can allow this to remain on the transformer. So these would be a leakage reactance values. In terms of the fault current, this is how long it can stay on a transformer. So what you would use this to determine is what sort of clearing time you would require for the transformer as part of your system. So interpretation, I have a transformer reactance of 7%, right? 0.07 per unit. And we are saying you have 15 times the fault current, the operating current, 15 times the rated current. Yes, they're saying that that should not be allowed to be on a transformer for more than 5 seconds. You have a 4 up to 25 should not be allowed for more than 2 seconds. Right?
Excuse me, sir.
Yeah.
These are, I'm presuming, the standardized ratings. These would be standardized ratings, or is it something that you get off the nameplate?
This would be what you would get for this particular unit. But we are giving you some examples of what would exist. So you'll be able to pick this up from the data sheet from a transformer.
Understood.
Well, I will not claim that I have the same headache as Ms. Gray, but I am beat, man. This has been my toughest semester in a few years. I don't know about you, but I want it finished fast, boy.
Same.
No, you must not agree with You're a student, you can't be tired. All right. I'm tired. I mean, how much weeks we have left? 2 weeks after this? When is your project due, by the way? Is next week? Huh? The 8th, yeah, next week. How is it going? Huh?
That when they are wonder too. So,
Well, it's in the first the PowerPoint that you shared with us the first day of class. The last couple slides.
I'm sure I gave you the project. Maybe I didn't give you the project. What can I give it now, Mr. Mr. Duncan? So you're telling me you haven't started anything as yet? Then I want to brave, so. No, but you don't want to have that messing with your major project, you know? And your preparation for your exams. Anyway, it's one group, right? So I suppose you all know what you're up to. Right. But I'm sure I gave you, man. If you understood the lab exercises, then the project shouldn't be a problem. Because it's really a follow-up from what you did in power systems. Right, Ms. Green, for those who have read it.
Yes, sir. Things are follow-up from the first lab that we did.
Yeah, man. All right, cool. So now we clear that up. And I'm not shifting the date, if that is what you're hoping. All right? And I know that's what you were working at, but sorry. Okay, so what this is saying to us, again, we didn't really spend much time on it, but the tripping will occur because of the time for tripping. It would be beyond that first cycle. So there's very little possibility of escaping the impact of the fault current. I hope you understand that. So if you think of the even the SF6, for example, SF6 breaker operates in 3 cycles, right? 60 seconds. Good. With that, because the fault current would be there for at least 2 cycles, it means that the full effect cannot be averted. So whether you like it or not, and regardless of the speed of operation of your protection system, the transformer will be exposed to high mechanical stresses from these fault currents. That's the point we're making here. All right? So it means that you then have to just manage, right, the stress that it will be exposed to. It's like building a skyscraper. Not that I know much about it, but if you're building a skyscraper in an area that is susceptible to earthquakes, you're going to build it so that when the earthquake hit, the skyscraper actually move. So you can't get away from it being exposed to the shocks. What you do is to build it in such a way that it moves with the earth movements. Yep. So that one is not something that you would be able to mitigate against from a design, meaning a protection system design perspective. All right, but that would have been taken into consideration in the design of the transformer itself. All right, because as I said, given when it is impacted and the fastest operation that we know, right, it will have that mechanical impact. All right. All right, next, for your overvoltages, you have overvoltage due to transient surges, and you have burst frequency voltage. So we can have, basically what we're talking about here is overvoltage as a result of whether switching or lightning, right? Or overvoltage just because the system is operating at higher voltages than expected. So for those who may have to consider the whole operation of taps, for whatever reason they may need to consider it, they would have to appreciate the fact that one of the benefits of the tap changers is to, well, I mean, it has already been said, it's to regulate the voltage, keep the voltage within spec. All right? So I want to keep it within that 5%. All right? So, oh my God, I tell you, I have given you guys a deal, still don't care about the transit. Every time I read something like this, I say I need to carry it to the substation. I'm sorry, students. I shouldn't even tell you this, but yeah, I'm carrying 2 major offices at work. All right? So I am your dean and your vice dean at the same time. I don't know. I suppose I should just try and go for the Trinity, but anyway. So a lot of things just keep falling by the wayside. But don't worry, I am committed to getting it done before. Because I want to put a sort of sheet over all that you have been doing. I find that when you go into the substation, usually I would carry you there before. make you a little confused, then carry you in class, teach you, and then carry you back. And it would make a lot more sense. This time we just go there. Yeah, I need to talk to Mr. Lee about that. Anyway, so at the top of your transformers, you would find the lightning arresters. And these are there not just for basic protection, but to prevent these over voltages that we are talking about. Because although it is not visible, it does create significant vibrations for your transformer and can therefore disrupt core bolts and that sort of thing, right? Which then lead to all sorts of winding faults. All right. For the power frequency, all right, what we're saying, it may occur simply by, well, changing in loading conditions. Yeah, I think I would keep it at that. Now, although this is what I was referring to at the time, but if the working flux increases and we have a proportional increase in magnetizing current, what this would trigger is a situation where you now start seeing more current going into your primary than what's coming out to your secondary. And yes, I know that the values are different, but in terms of the turns ratio of the transformer as well as the turns ratio of the CTs, the current in will be equal to the current out. All right? But what we are saying now, if you are seeing an increase in the magnetizing current, that current that is being taken in from magnetization is not adding any or providing any useful benefit to the load. All it is doing is going in to supply flux to the core. So when you look at your differential system, what it will be saying to you is that you're getting more in, you're getting less out, therefore the fault is on the transformer. So you run the risk of the transformer tripping for this reason. Well, not the transformer, but the protection system for the transformer operating. Alrighty then. All right, so the impact here is that you end up, I think I skipped one there, yeah. All right, so we spoke about the over voltages, yep, the impact of the magnetizing current. And then the last point we have there. So once you, and I mean, if you take it from the simple that you have looked at from your in high school when you looked at the core of your transformer, you realize that there are tightly stacked. The laminations are tightly stacked. Right? Now, if you were to have situations where core bolts are loosened, then it means that you're running all sorts of risks in terms of, additional vibration, damage to core, and then resulting in fault. Okay. Similar issues can arise from the having a low frequency. This summary statement is suggesting to us not that high frequency and high voltage is okay. What we're saying is that because low frequency negatively impacts the transformer, what you are getting is a worse scenario if you're gonna have the low frequency and the high voltage. So the high voltage affects it. Low frequency affects it. It is better to have the high voltage with the high frequency, but not the other way around, meaning high voltage with low frequency. Okay, so I have hinted at it quite a bit this afternoon. So let's talk now about differential protection for your transformer, and let's look at some key things. So we mentioned before that differential protection provides the best overall protection for your transformer. All right. But if we think about the differential system, we're talking about equality between input and output. That's how it operates. And if there's a deviation, then we know that the fault is on the protected unit. But the transformer is kind of unique. Yeah? I mean, I've given you quite a few of the answers already since this evening. But I want to now put them in context of the differential. Right? So we understand how a differential system works. Now we're going to look specifically at the design of your transformer and how it will then force us to take into consideration the operational features of your transformer. All right, so first challenge we have as far as differential is with respect to magnetizing inrush current. All right, and as I said before, if you have a transformer that is de-energized, once you re-energize the transformer, there's going to be a certain current coming in the input, but there won't be a commensurate output current. All right? Just excuse me a second, please. I will be back in a minute.
Recording stopped.
All right, sorry about that. I just was extremely thirsty, man.
Recording in progress.
All right, so as I said, magnetizing inrush, it's a normal phenomenon because for the transformer to work, you understand the whole business of mutual induction, right? You have to create that magnetism within the core in order to get the output at your secondary, okay? But at the time of energizing the transformer, all the current that is taken in will be used for magnetization purposes. So you won't get a commensurate output. So the differential system, based on its construction or design, would see that as a fault because there's current coming into the transformer, but there's nothing going out to the load. All right? So how do we treat with that? We treat with that. Huh? Well, before we deal with the treatment, are you familiar with the hysteresis loop? I know it is formed.
You introduce it to us.
I introduce it to you.
Couple weeks
All right. All right. Let me go over it quickly then. We start at the origin. All right. And what we do is to magnetize. So you would have the magnetic. All right. So that's the magnetic curve, magnetizing curve. You then reverse the current. And so in reversing the current, but when it gets to this point, and the flux there would represent the amount of magnetism that is retained. In reversing the current, now this is the signal you're putting in. So you're putting in an AC signal, right? So from 0 to peak, you're bringing it up. Bringing it back to 0, yes? And then when you reverse it, you get it to this point. Now, this portion, let me try and get another color ink. This portion would be a residual flux. All right? This. I don't like how this one's there. Because the width is supposed to tell you the remnant flux. So it looks like this one has it on the wrong axis. Current is normally on the vertical axis. Anyway. So the width tells you the amount of flux that is retained. Right? And the length, why do I feel confused? Do I sound confused? Maybe I shouldn't have drank any water. The width is supposed to give you the coercive force, and that is the amount of flux, that is the amount of current applied in the reverse direction to wipe out the flux, right, to bring the flux to 0. All right. But anyway, the bottom line is, in the cycles of magnetism, in the cycle of magnetism, you magnetize by increasing the current, right? And you saturate here. Right? Then you reverse the current. Right? You reverse the current. And this now gives you the width, therefore gives you the amount of residual flux. In bringing this to reversing the flux, yes, that's the amount of current required to reverse the flux. and you continue there. And then when you go go back up, oops, sorry, you're increasing. All right, so this gives you the full cycle. So this is what you're doing. You enter, that is the maximum. You reverse it down here, right? And then you increase again. So there are 4 cycles. Increase, reverse, increase in the negative, which is when it comes to this point, and then increase again, right? So it comes to this point, and then the cycle starts again, all right? So what this does is say to us that the wider the curve, it is telling us that it is retaining more magnetism. The longer the curve, it is telling us the coercive force. So what you want in the core material for your transformer is that it is easily magnetized, easily demagnetized, but you also want it to retain as much of its flux as possible. So in other words, you don't want, the more energy you use to demagnetize it, it's going to be using more and creating more core losses. So you want to use less energy to remove the magnetism, all right? Now, what in showing this, what we are saying is that that magnetic cycle has to occur within the core before you start seeing an output. But to do this, you require input. And that's the magnetic inrush, because it is coming into the transformer for the sole purpose of creating the magnetism. All right? Now, to mitigate against this, all right? There are 2 things, or 2 primary ways that we use to ensure that differential system does not operate. One is that the inrush current has what we refer to as significant second and third harmonic components. All right, so this is what you would now go back to. Remember this thing, huh? I know you have forgotten it already, but it's all right. Huh? And there was a topic we did called you remember that thing, right? I'm just writing it. I mean, you may have forgotten it. But anyway, we did another thing called complex waves. All right? And what you would have done is to do the harmonic analysis on the complex wave. And you would find that the second harmonic and the third harmonic in a magnetic inrush wave is much higher than a normal primary current. So because we are able to make that determination, we can then use what are known as harmonic restraint coils. So once the system detects these harmonics, right? Once the system detects these harmonics, then it would not operate, because it would recognize that the current at the input are inrush currents. Now, if it was a fault, if there's a fault on the transformer, then the current going in would not have these harmonics, and so the differential would trip. If it's a true fault, the differential would not trip. However, your overcurrent system would. We understand that?
You can say that again, please.
All right, so the three scenarios. One, if it's inrush, then you will have the second and the third harmonic components. And we're talking now about the primary current. All right? So the harmonic restraint coils would detect that it's magnetizing current and would therefore not operate. So that's one. Two, if it's an internal fault, then the presence of the second and third harmonic currents would not be there. And so it would operate. Three, if it's a through fault, meaning the current is only passing through the transformer, then the differential will not operate because the current coming into the transformer would be equal to the current leaving the transformer. However, that through fault would be managed by the overcurrent system on the transformer. So you're going to limit the magnitude of the current that can pass through your transformer. That's what we're saying. All right? So we have dealt with inrush. Now, the other method, and I mean, I put this in because it was what I did in my my master's degree, which is that instead of using the harmonic restraints, we then use wavelet transform, which is quite similar to Fourier analysis. Because you know, of course, that the harmonic analysis is really based on Fourier. Yeah, Fourier analysis. But the wavelet analysis is the same principle. However, the term wavelet just means little wave. And what you would, you have this toolbox. You have a wavelet toolbox in MATLAB that you can then use to determine whether or not the current seen going into the transformer is fault or inrush. All right, so the wavelet is just, you know, a more, for use of a better word, a more refined method of determining or identifying the type of waveform. All right?
Excuse me, sir.
Yes.
So is it that then the harmonic restraint coils, if that's the correct name, would no longer be used in this?
For the wavelet, you would then, remember what you're trying to do is to determine which input current, which primary current is a fault current. That's your key focus. So in terms of the wavelets, these would be defined for different types of operation. So if it is regular inrush, certain wavelets would define inrush current. If it's a fault current, certain wavelets would define that. So when you see the wavelets, then you would have restraint. But we wouldn't then call it harmonic restraint because it is not doing it based on the second and third harmonics. So you are using the restraint mechanism based on the wavelet analysis. I don't know if that makes it any clearer. So I would only call it harmonic restraints if I'm detecting harmonics. And then using that information to make my decision. For the wavelets help you to identify individual waves. So it identifies this input as inrush. It identifies another one as regular input current, or it identifies it as a fault current. So in terms of the inrush, this is what it would look like. Right? And if you were to do the harmonic analysis on that, what we are saying is that you would see the second and third harmonics as being more pronounced than the regular input current. All right. So the first thing we looked at was inrush in terms of the design of your transformer and how it affects differential. The next one, different voltage levels. Because that's what a transformer does. It connects systems of different voltages. And to mitigate against that, we use the ratios of the CTs, yes, to produce the same currents on either side. All right? So if we have a transformer S, the CT ratios are chosen such that on the low voltage side and on the high voltage side. Right? So if we have a given rating S MVA on the low voltage side and on the high voltage side, those are the currents. So to better understand what we are saying here, we have a 13869 kV transformer and the MVA rating is 50. Okay? So the current on the high voltage side would be 50 over root 3, 138. So we get 209 amperes. And on the low voltage side, all right, on the low voltage side, we get 480, which is expected. Right? The lower voltage will give you the higher current. Since this is a 2-to-1 transformer, then the current would also be in the ratio 2-to-1 or 1-to-2. All right? So the CTs that will be chosen, will be twice. So we get the same 4.18 on either side. Is that clear? So, you finish with that?
Yes, sir.
All right, so generally, if you have a transformer of turns ratio, K to 1, that's from the primary to the secondary, the turns ratio of the CTs. On the primary to the N over K to 1, and on the secondary, N to 1. So in that example, the turns ratio was 2 to 1. So on the primary, whatever we would have chosen for the secondary would have used half on the primary. So if I chose the 500 to 1 or 500 to 5, it should be 100 to 1. Okay? So if I choose the 500 to 5 on the secondary, then on the primary, it would be the 500 over 2. So that's why we use the 250. Let's go back to the example. So this would be the 250. The N to 1 would be the 500 to 5. All right? So that's the second issue. So the first issue is inrush. The second one is the fact that we have different voltage levels. But we do that by the choice we make for the CTs. All right? The next issue we have for your differential system is that you have a phase shift for your delta Y connections. So we know for your delta Y, there's a phase shift of 30 degrees, yes? What we do is to reverse the connection of the CTs. So if the transformer is delta Y, then we'll connect the CTs Y delta. All right. So in terms of the connection, I don't know if you can see that clearly. So on the right-hand side, we have delta. And we have star, sorry. What am I telling you? This is not a good evening for me at all, boy. Anyway, you have star on the right. You have delta on the left. All right? So where you have the delta winding, you connect the CTs in star. Where you have the star, you connect the CTs in delta. All right? So that's what you need to remember. So to deal with the phase shift, we reverse the connections of the transformer. So again, I repeat, the first issue we have with the transformer, inrush. The second one, the difference in voltage levels. The third one is the star delta phase shift. All right? And then the last one, transformer taps. Now, I showed you there, right? In the figure, I didn't highlight it, but there were some, you saw some little circles just above the relay. Those were bias coils. But what we're saying, if you're using taps, right, it means that the differential system would operate in such a way that it would facilitate the deviation based on the tap voltages or the tap settings. So there would not be a strict adherence to one-on-one matching on either side. You would have the bias coils which would allow that variation about the mean voltage. All right. So those are the 4 conditions. And I think that those 4 conditions are riveted in your head, right? We don't have a problem with them, right? Good. Okay. Now, we mentioned them earlier, but didn't speak to it much. We mentioned the use of fuses. Yep. So, and you already had, I'm sure I gave you an assignment on fuses. I gave you an assignment on fuses and breakers, right? A reading assignment. Okay. So for your distribution transformer, there's some information here. In terms of the rating, the start of full load current that we're dealing with, rated current and the operating times, right, at 3 times the ratings. The thing you need to remember, what I wanted to appreciate is the fact that this sort of data is available. All right? And then lastly, this evening, low oil. So you have oil level indicators. So if there's somehow a leak on the system, therefore causing the oil to escape, and I dare say you will actually go into the substation and see areas around the transformer looking greasy. You will see it. It requires some attention. But once you get to low oil, it means that you are now exposing the windings. And it needs to be attended to immediately. So you have those indicators. All right? I mentioned earlier the whole business of the interturn faults, but I didn't really speak to the how we treat with that. So you have what is known as a Buchholz relay. Did I go through that with you before? I gave you as an assignment? Oh, okay, good. All right. So in terms of the faults on the oil, they are going to cause the oil, technically speaking, to boil, therefore producing gases. And once the gas rises, then it will remove that cushion below the ball in your Buchholz relay. All right? And your Buchholz relay have different settings. So the ball drops slightly, it sends an alarm. And it continues to escalate the further down it goes until it gets to a point where it will trip the transformer. Right? But at least it gives you an opportunity to remove the transformer from fault, from service. You can bring in a portable transformer. Yes. Remove the faulted one from phase, from operation, and then have it repaired and replaced. And I'm speaking against the background of you not wanting to impact customers, right? And I am assuming that that is where we are at in our lovely country. All right? One of the there's a project that was being done some years ago by Mr. Sinclair, where what they did was to use transformer oil to determine whether or not there were faults within the transformer. So because if there is a fault, it would create these hydrocarbons. Yeah. It means that you will start the color of the oil will begin to change. So on the transformer, there's a little, for use of a better word, there's a little pipe at the side where you can release some of the oil for testing. And that is a test that is done quite regularly as part of the maintenance process, to release the oil and look at it to determine whether or not you're having any fault occurring. Okay, so you have already looked at the buckles, so I don't need to address that tonight. All right. Okay. Yeah, that's it. That's it for tonight. Can't wake up now, Miss Gray. Why am I harassing you, Miss Gray? You can report the lecturer. Report him to the dean, yeah? All right. All right, so I will pass your names on to the OUR, and you should be getting an invitation tomorrow. All right, so have a good evening. So Duncan, I shouldn't put your name. Where you have for Thursday? Can you guys give me somebody else? I need 5. I have 4 already. All right, I'm gonna fill out my spreadsheet and hopefully you'll send me an email soon. All right, have a good one. Take care.
You too, sir.
Later, sir.
Good.
Recording stopped.